Welcome to Orbital Dynamics Part 43. This part is based on excerpts from the book, The Mechanical Universe. With the formalisms we derived in the previous section, we can characterize circular motion as viewed from an inertial frame where some physical force supplies a centripetal acceleration, and from the rotating frame where there's a centrifugal force. We call a centrifugal force an inertial force. It occurs in frames that rotate in uniform circular motion with respect to an inertial frame of reference. The Earth in its daily rotation is a good example. Let's set up an example. Imagine a mass, m, at the end of a rope. The rope represents the position vector r. The mass is being spun in a uniform circular motion. We learned from part 34 that the velocity of the mass, v of t, is tangential to the circular motion, and it equals r times omega, where omega is the angular speed expressed in radians per second. The acceleration is minus omega squared r, which equals minus v squared over r. The net force is mass times acceleration, and it's in the direction opposite to the unit vector r. That equals minus the unit vector r times mv squared over r. That characterizes the tension in the rope. Without that, the mass would travel in a straight line along the velocity vector. The centripetal force caused by the tension in the rope keeps the mass traveling in a circular path. These equations hold if you're in an inertial frame of reference observing the rotating mass. Now let's consider the frame of reference within the rotating mass. In this frame, the mass doesn't move. It also doesn't rotate. The rest of the world does, but the mass doesn't. You'd experience this on a rotor ride at an amusement park like in this picture. On that ride, you stand against a circular wall, and after it spins up, the floor drops out. You stay stuck to the wall because there's an inertial force holding you and the rest of the people up against the wall. That's centrifugal force. Since the rotating mass from the rotating frame of reference isn't moving, there has to be a force that balances the tensional acceleration imparted by the rope. Here we invoke Newton's third law. For the mass to be motionless, there has to be an equal and opposite force. That's simply the unit vector r times mv squared over r. It points radially outward and is therefore called the centrifugal force. The centrifugal force is m times acceleration a. That equals mv squared over r, which equals m omega squared r. If the angular speed omega is increased, the force increases. If the distance from the axis of rotation increases, the force also increases. The forces acting on a circular body can always be described either in an inertial frame or in the rotating frame. In the inertial frame, there is no inertial force, only a centripetal force. The tension on the rope keeps the mass in constant circular motion. In the rotating frame, there is an inertial force that causes an apparent acceleration outwards. That's a centrifugal force. The Earth rotates. If the Earth were exactly spherical and did not rotate, the wave of an object would point directly toward the center. Let's look at the wave of an object of mass m situated at latitude theta on the Earth's surface. For a non-rotating Earth, the only forces on the object would be the gravitational attraction mg of the Earth towards its center and the push n of the Earth, which would be equal and opposite to mg. We call the force n the weight of the mass. There have to be counteracting forces for the mass to stay in place. On a rotating Earth that is spherical, the true gravitational force mg still points directly towards the center c, but now the centrifugal force F sub c also acts on the object. The centrifugal force F sub c is equal to m omega squared r times the unit vector r. This force is directed outward perpendicular to the Earth's axis of rotation, not outward from the Earth's center. Big R is the Earth's radius. Little r thus equals big R times cosine theta. The centrifugal force in terms of big R is m omega squared times big R cosine theta times the unit vector r. The sum of the forces is thus mg plus m omega squared r cosine theta times the unit vector r plus n. It's slightly changed from n as a result of the centrifugal force. Because the mass is not moving, the sum of the forces is zero. We can express this as n equals mg plus m omega squared r cosine omega. We can then substitute mg for n. If we take the sum of these two vectors, we get the net force vector. The angle theta is here, and it's also here. We'll use the law of cosines to determine g. Here's the law of cosines. If we plug in values, here's how we derive mg. Let's plug in the formula we derived for Fc. M omega squared times r cosine theta. There are common terms, m and cosine theta, that we can combine, and we can factor out the mass term, m. The formula for g would be the square root of this. This is the formula for gravitational acceleration g at a given latitude theta. Let's do a real computation. The standard gravity of the Earth is 9.80665 meters per second squared. If theta equals 90 degrees, we'd be at the North Pole. The cosine of theta is 0. Let's make that substitution into the equation for g. The second and third term are multiplied by 0. That results in this. G equals the square root of g0 squared. Hence, g equals g0. Let's go to the other extreme, where theta equals 0. The cosine of 0 degrees is 1. The equation for g simplifies to this. The angular velocity of the Earth is 2 pi radians per day, and there's 86,400 seconds in a day. That equals 7.2722 times 10 to the minus 5th radians per second. The radius of the Earth is 6,371,000 meters. If we plug in those values, we get this. If we do the calculations, we get this, and that equals the square root of 95.51068. And that equals 9.77296 meters per second squared. That's a 0.34% difference. At the equator, you'd weigh 1/3% less than you would at the poles. An average male weighs 80 kilograms, which is 180 pounds. At the equator, he'd weigh about 1/4 kilogram less. The reduction in g due to centrifugal force is greatest at the equator and 0 at the poles. The variation of g with latitude follows the equation, but the measured effect is about 50% greater. This is due to an equatorial bulge of the Earth, another consequence of the Earth's rotation. The measured values of g range from 9.831 meters per second squared at the equator. We'll talk about that in the next section. The observed dependence of g on latitude establishes that the Earth is not an inertial frame. Which frames are inertial? Inertial frames are at rest or move at a constant velocity. You can think of this with respect to fixed stars or distant galaxies. On large scales, the distant galaxies are rather uniformly distributed throughout space and provide a definite frame of reference. Although, if you need to be very precise, you'll find that distant stars and galaxies are also moving, and they're accelerating relative to us. It turns out that there is no body or object that's inertially fixed in space. An inertial frame of reference is hypothetical. You might be able to travel at a constant velocity, but you'd never be able to stop rotating.